gradually progresses through the metal. The crack deepens and weakens the part as it goes. In relatively ductile metals, each stress application high enough to cause a crack to grow forms a tiny ridge-like striation at the tip of the crack. These striations are frequently visible in electron microscope examination of the more ductile metals. They are actually growth marks, analogous to growth rings in trees. These striations are characteristic of fatigue fracture in many metals. However, the striations are not always present, especially when the metal has little ductility. They are also easily damaged by corrosion, mechanical action, or post-fracture damage. Two sets of striations can be seen. The widely spaced striations are caused by a higher stress. The more closely spaced are lower stress. The striations never cross. They are generally concentric or parallel to each other. Each striation marks the tip of the crack at some point in time during the test or service life of the part. The striations are very small, microscopic ridges and should not be confused with the much larger macroscopic ridges called beach marks, which may also be seen at very low magnifications. A very large number of microscopic striations may exist between each pair of macroscopic beach marks. The striations represent the repetitive cyclic strains on the part. The beach marks represent gross changes in the operation of the part. The final rupture stage is not really fatigue at all. Stage 3 is simply fracture, the last load application by which complete separation occurs. This final rupture may be either ductile or brittle, depending upon the properties of the metal. The importance of stage 3 in the analysis of fatigue fractures lies in the observation of the size, shape, and location of the final rupture. Size, shape, and location help identify the type of stress, its direction, the relative stress, and the strength of the metal in the part. This is a bending fatigue fracture of a large threaded shaft. The fracture began at a groove on the surface of the shaft. The beach marks indicate that the fracture proceeded almost entirely across the section before the final separation. Fatigue fracture characteristics. Macroscopic examination can reveal many characteristics of a fatigue failure. And of course, a macroscopic examination can be done at or near the failure site. A macro exam is particularly useful in correlating fracture surface characteristics with the size and shape of the part and with the loading conditions. The crack origin location may be found by first viewing the fracture surface at a low magnification between 1 and 100 diameters. The most common macroscopic feature characterizing many, but not all, fatigue fracture surfaces are the beach marks. Beach marks are centered around one or more sites corresponding to the fatigue fracture origin. When present, beach marks provide valuable information: the point of origin, the relative load intensity, and the crack dimensions at final failure. However, fatigue fractures will show beach marks only if one or more of the following factors were present: interruptions in service, large changes in loading magnitude or frequency, or oxidation or corrosion of the fracture surfaces during rest from intermittent service. Here, the beach marks in an aluminum alloy were produced by changes in the growth rate of the crack. These were the result of variations in applied load levels. The final fracture region covers about 40% of the fracture surface. A 4130 steel shaft failed in service. The fracture surface exhibits beach marks produced by oxidation of the fracture when the shaft was idle. The beach marks shown here were produced by a combination of variations in loading and the periods of rest normally experienced by an automotive crankshaft. In this case, the crankshaft is a ductile iron. Fracture originated at a notch in the root of a repair weld. The final fracture area was very small, indicating that low load levels prevailed. Under conditions of uninterrupted, constant amplitude loading, beach marks will not be evident. This fracture surface of a specimen tested in a laboratory shows the load was repeated at the same magnitude and without interruption until the final fracture. The fracture surface produced by the fatigue contains no beach marks. This condition is common in continuous laboratory fatigue testing or in continuous service. Examination of fatigue fractures by light microscopy is sometimes difficult. The features of the fracture surface may be high and exceed the depth of field of the microscope. Metallographic examinations of cross-sections through suspected fatigue fractures typically show a transgranular crack path. However, intergranular fatigue fractures can occur in hardened steels at low stress levels. A cross-section through a crack that has not grown enough to cause separation is often useful in showing deficiencies in design or manufacture, or the results of unanticipated service conditions. Electron microscope examination of undamaged fatigue fracture surfaces in materials up to about HRC 50 frequently shows finely spaced parallel ridges or striations. These fatigue striations are oriented perpendicular to the microscopic direction of crack propagation. With uniform loading, the spacing generally increases as the striations progress from the origin of fatigue. Each striation is the result of a single cycle of stress, but every stress cycle does not necessarily produce a striation. The spacing between striations depends strongly on the level of applied loading. The clarity of the striations depends on the ductility of the material. Striations are only visible in relatively ductile materials. Patches of fatigue striations in high-strength steel are less visible than in a wrought aluminum alloy or in low-strength steel. On the microscopic scale, the most important feature of the fatigue process is the nucleation of one or more cracks under the influence of reversed stresses that exceed the flow stress. Subsequently, fatigue cracks propagate by a series of opening and closing motions at the tip of the crack, producing the striations which form within the grains. The cracks initiate points of maximum local stress. These points are determined by the shape of the part or by surface and metallurgical imperfections, such as scratches, burrs, or other fabrication flaws. Foreign materials and hard particles in the metal can also determine the site of crack initiation. A great number of fatigue failures in otherwise lightly loaded structures originate in fretted or rubbed areas. In any jointed structure with some relative motion at an interface, fretting provides a possible location point for the initiation of failure. On the macroscopic scale, early crack extension occurs under conditions that give a typical smooth-textured, grained, flat-faced surface to the fracture. When produced under random repetitive loading or sequences of high and low stress amplitudes, the characteristic beach marks frequently result. It is possible for a fatigue crack to originate in the hard, strong region of a part and propagate into softer, weaker regions. This is usually due to heat treatment, imparting intentional variations to the properties of the material. Several different types of fractures may exist. In this induction-hardened axle, the fatigue origin was at the induction-hardened surface, heat-treated to about 46 HRC. The stress is concentrated in a fillet located at a change in the shaft diameter near a keyway runout. The fatigue crack gradually progressed around a large, roughly circular area. The shaft became so weakened by this large stress concentration that only one additional torsional load application was necessary to cause the final rupture. The well-defined chevron marks in the relatively hard, brittle induction-hardened zone around the surface point toward the fatigue fracture origin. Inside the shaft, the considerably softer core shows a rough surface, characteristic of a rough tensile fracture in a ductile metal. This fracture is at a 45-degree angle to the shaft axis, typical of the fatigue and brittle fractures of shafts in torsion. When a crack has grown to the size at which it significantly reduces the load-carrying capacity of the part, a change in the direction of crack growth usually follows. In many parts, the fracture may, in general, still appear flat, but if the level of operating stress is low, the surface appearance becomes rougher and more fibrous. This indicates the change from crack extension to the final fast fracture. Notice there are no beach marks in the fatigue area. This is because the cycling in the test was continuous. As a general rule, low stress, high cycle fatigue produces flat face fractures. The fracture surface appears fine-grained and lightly polished near the crack nucleation site. This is where the stress intensification is least. As the crack grows and the intensity of stress increases, the surface becomes progressively rougher. In torsional fatigue caused by high stress, low cycle loading, the general direction of fracture is at 45 degrees to the axis of the part. The surface is fibrous and rough. This same rough, fibrous appearance is found in certain areas of many fatigue fractures. The effects of variables. When analyzing fatigue failures, the effects of variables are constantly kept in mind. Variables affecting a failure include overstress, stress concentrations, frequency of loading, mean stress, type of loading, and residual stress. The nucleation and growth of a fatigue crack are strongly affected by the shape of the part, the loading exerted, and the features on the fracture surface. Fracture analysis is relatively simple in a beam of uniform cross-section subjected to fluctuating or alternating stresses. The appearance of the fracture surfaces in test specimens is predictable. First, consider unidirectional bending. A beam of uniform cross-section subjected to pure fluctuating unidirectional bending has a bending moment that is uniform along the length of the beam. The tensile fiber stress at the surface is also uniform along the length of the beam. At high stress levels, fatigue cracks may initiate at several points along the beam on the tension surface before one of them becomes large enough to cause the final fracture. At low stress levels, only one origin is usually found. A related form of loading is cantilever loading. Here, the bending moment varies along the length of the beam. This means that the tensile fiber stress will also vary along the length of the beam. Fracture will initiate at the point of highest stress, usually adjacent to the rigid mounting, depending on the shape of the beam. Because of the shear stress component characteristic of cantilever loading, the direction of the maximum tensile stress makes a small angle with the axis of the beam. Consequently, a fatigue crack will usually propagate into that portion of the beam within the fixed mounting. Next, consider reversed bending. Reversed